Welcome to the training session on the Enterprise Rain Rate Baseline product, also known as Self-Calibrating Multivariate Precipitation Retrieval. Bob Kuligowski is the developer of the product. I'm Dan Bicus, and I'll narrate this training. For our learning objectives, we're going to briefly describe the Enterprise Rain Rate, or ERR, algorithm, describe strengths and limitations of the ERR algorithm, and also analyze example imagery of the ERR product in AWIPS. Estimates of instantaneous rainfall rate are output every 10 minutes at full ABI IR pixel resolution with a latency of less than 5 minutes and are available over the full disk day and night since IR bands are utilized. Rainfall rates up to 3.9 inches per hour can be output by the algorithm. The motivation for this product can be easily understood by first understanding the differences between satellite-based rain rates derived from a microwave instrument versus that from an infrared instrument. Microwave-based rain rates are generally more accurate than IR, but less timely since they're on polar orbiting satellites. Meanwhile, IR-based rain rates are generally less accurate than microwave, but more timely than microwave since they are available from geostationary satellites. The solution is to use the more accurate microwave-based rain rates to calibrate an IR algorithm and thus optimize the accuracy, frequency, and timeliness of the product. The GOES-R rainfall rate product makes use of GOES-R ABI bands and is calibrated against the CPC combined microwave field known as MW-COM. The ABI bands used as input are bands 8, 10, 11, 14, and 15. These bands contain information about the cloud phase and particle size and help to discriminate. The algorithm derives rainfall rate in 2 steps. First, identify pixels that are experiencing rainfall. Using a matched dataset of ABI, IR, and microwave rain rate data, use discriminant analysis to determine which ABI, IR bands are most skillful at discriminating between raining and non-raining microwave pixels and the required threshold predictor values. And then for the second step, retrieve rainfall rates where rainfall has been detected. This is done using a matched dataset that contains only raining microwave pixels. Use stepwise forward linear regression to determine which ABI IR bands, or band differences, have the strongest relationship with microwave rain rates. To account for nonlinear relationships, each ABI IR band is also regressed against the microwave rain rates in log-log space to form a supplemental set of predictors. The distribution of rainfall rates is then adjusted via a lookup table to match the distribution of the microwave rain rates. And finally, an adjustment based on the mean GFS relative humidity over the lowest 1/3 of the model domain accounts for evaporative losses in dry regions. Several assumptions are made when estimating rain rate from IR data. One is that the cloud top temperature is related to cloud top height. Another is that the cloud top height is related to the strength of the updraft transporting moisture into the cloud, and further, that updraft strength is related to rainfall rate. Generally speaking, colder clouds are associated with heavier rain, and warmer clouds are associated with light or no rain. The performance of the rain rate algorithm is improved when the data are divided into 3 cloud type categories based on thresholds between the various band brightness temperatures given here. They are called water, ice, and cold top convective clouds, but these are not exact classifications. The purpose is to separate clouds with different relationships between the IR brightness temperatures and the rain rates. Separate calibrations are also applied over 15 by 15 degree lat long regions, which yields 330 distinct rainfall classes in the algorithm. The additional spectral bands provide information on cloud phase and particle size. When using satellite QPE, it is critical to remember that while our primary interest is in rainfall rates at ground level, satellites detect cloud top or cloud level characteristics. One of the differences between the two can be location. In sheared environments, rain rate shafts are not vertical, so the surface rainfall can be displaced by up to a few pixels from the locations indicated by the IR imagery. Pixel locations are adjusted for parallax, but small errors may still occur in the case of incorrect cloud height assignments. Also, satellites cannot directly observe orographic effects and subcloud phase changes. Some of these issues can be addressed with the help of NWP model data. Now we'll review strengths and weaknesses of the product. Satellite rain rate estimates are best for deep convective rain and perform poorly for stratiform precipitation. Weaknesses of IR retrievals include underestimating or missing shallow stratiform clouds that are near or warmer than 15 degrees Celsius, which can include orographic clouds or very shallow convective clouds, such as trade wind showers. Also, cirrus associated with convection can be incorrectly identified as rainfall regions, even with the help of additional spectral bands. Here's the Enterprise rain rate product depicting convection over and near Arkansas. Remember that the Enterprise rain rate product will do well for deep convective rain, but it will incorrectly identify anvil cirrus as raining. Ideally, you would want to look at the Enterprise rain rate product in tandem with other datasets, since there are strengths and weaknesses of each data type that can give the best possible analysis when used in combination. Of course, over the CONUS, radar data offers high-quality rain rate data, but if the radar data is unavailable for whatever reason, the GOES Enterprise rain rate product is available. I show the MRMS surface precipitation rate, or SPR, in the lower right panel to illustrate the effect of anvil cirrus incorrectly being identified as raining. The anvil cirrus can be readily observed in the GOES IR imagery in the lower left panel. In the upper right panel, I show the blended rain rate product, which combines data from GOES along with data from microwave instruments on polar orbiting satellites. Data from microwave instruments generally provides a better estimate of rain rates compared to data from GOES. However, the data is only available hourly, which is less than ideal for this scenario with rapidly evolving convection. The 10-minute product update for the Enterprise rain rate is key for rapidly developing convection. One situation that is ideal for using the Enterprise rain rate product is over oceanic regions where radar data is not available. Whether it's the case depicted here, which is an extratropical cyclone near Hawaii, or a tropical cyclone over the Atlantic Ocean, this product provides valuable data where radar data is not available. Something to keep in mind is that the version of the product on AWIPS prior to March of 2025 utilized the algorithm version from September of 2010. Known limitations of that version include the following. It did not update its calibration in real time, which will degrade its accuracy somewhat. Also, there are occasional inconsistencies in rain rates between different types. A symptom of this could be holes in deep convective clouds. Also, it did not account for subcloud evaporation of rainfall, which means it tends to overestimate rainfall in relatively dry environments. These issues are all addressed in the new version, although inconsistencies in rain rate between types still happens on occasion. In summary, satellite rainfall estimates are informative, but must be understood to make the best use of them. Use the Enterprise rain rate product in tandem with other data for the best possible analysis of rain rates. Weaknesses can be overcome with other data, and strengths can add value to or supplement other data.